Hi everyone, today I would like to present Causality-preserving Asynchronous reality. The authors of this work are Andreas Fender, which is me, and Holz. In the current digital age, we got used to asynchronous communication services like email and instant messengers. The advantage of asynchronous communication over synchronous communication is that the recipient can choose when to process a message or mute notifications to avoid distractions. In contrast, interacting in a physical workspace is always synchronous. While such co-located interactions are important for socializing in workspaces, they can also lead to interruption of coworkers. We explore a future in which immersive technology is commonplace. Asynchronous reality means that immersed users are able to freeze time around them, for instance when they want to work on a task that requires focus. This creates a time bubble, which means that time only flows within the personal space of the user. The time in the room is frozen until the user is finished with the task. When time unfreezes, the user quickly catches up with reality. To explore the concept, we implemented a prototype system called Async Reality. We combined a network of Azure Kinect cameras with an Oculus Quest 2 virtual reality headset. We also attached a RealSense camera to the headset. Based on our prototype system, we acted out a scenario. Let's take a look at the first part.
The scenario takes place in a small game studio. The team is in the middle of their current project. To promote the game, they want to release an action figure that is based on one of their game characters. They already want to start developing the action figure so that it can be released at the same time as the game. Today, they want to create a 3D printed prototype of it. There is already an animated in-game version of the character. Two team members, Joe and Anna, discuss how to make it suitable for 3D printing.
Right now the model of the character is one connected mesh.
They conclude that the model needs to be split into 3 parts. Joe then returns to his desk and starts creating the 3D print version. After sending the models to Anna, Joe wants to work on the game logic for the rest of the day, so he turns on focus mode. To block distractions, noise is played back for Joe and only objects in close proximity are rendered. While Joe is focused on programming, Anna prints the individual pieces one by one. After some time, the first piece finished printing and Anna brings it to Joe's office.
Hey, the skull is done now. I'll just put it here on the table, and you can take a look at it when you have time.
Let's rewind for a moment. Joe is in focus mode, so Anna's message is automatically recorded without him noticing. Our system stores asynchronous events including the recording and changes that occurred in the room, in this case the skull on the table. Instead of notifying Joe, the system renders those changes as glossy shapes. At some point, Joe takes a break and turns around. He decides to check the new object on the table.
Hey, the skull is done now. I'll just put it here on the table, and you can take a look at it when you have time.
The object is now up to date in Joe's reality and he can freely inspect it and interact with it. Afterwards, Joe resumes to his programming task and returns to focus mode. From then on, every hour or so, Anna drops by with another printed piece or some comments.
Hey, the left wing is done now. Let's check whether it fits. Seems alright. Could have been a bit better maybe. But I'll just put it here for now, and you can take a look at it.
This second event introduced 2 changes. The skull from event 1 was moved and the left wing was added.
Let's stop here and take a closer look. The arrow indicates that the skull from event 1 is a causality for event 2. This is because Anna interacts with the skull in event 2, so this event cannot happen before event 1, in which she brings the skull to the room. Throughout the scenario, Anna brings more objects and manipulates existing ones while Joe keeps programming. This leads to an instance of a causality graph, which ensures causally correct playback once Joe leaves focus mode and catches up with reality. Let's take a look at the general components of a causality graph. An event contains a recording as well as manipulations, which can be something like added or moved objects. There is at least one such manipulation per event. The first type of manipulation is a trigger. These are manipulations that no future events depend on. For instance, if a physical object did not change since the event, then it is stored as a trigger. There can be any number of triggers and it does not matter which one the user approaches to trigger event playback. The other type of manipulation is a causality node. Those are manipulations which are also causalities for at least one future event. An event can have any number of causality nodes. Each causality node has a causality for one or more future events. Lastly, an event can depend on any number of causality nodes of previous events. We developed an architecture to turn causality graphs into practice. This overview shows processing steps, data, and point cloud renderers, if conditions within the data flow are diamond-shaped. The primary input of our system consists of the RGBD streams that capture the room. In the case of our scenario, those streams come from 3 Azure Kinect cameras that capture the whiteboard, the table, and the entrance. We apply some pre-processing to smooth the input and remove noisy edges. The subsequent steps depend on whether the user is in sync with reality or not. Out of sync can mean, for instance, that the users in focus mode are currently catching up with reality. If the user is in sync, we simply render objects and people of the environment live. This means that users can interact synchronously. If the user is out of sync, then we use the asynchronous pipeline instead of rendering the point cloud directly. We first subtract the current background, which is a snapshot of the room geometry including objects. Our event detection checks whether the RGBD frames differ from that background. If that is the case, we start recording the incoming RGBD frames. While recording, we also keep track of regions where depth values are close to the background. For instance, when a person touches or moves objects. We call this the traces of the event. Once the system does not detect movement for a short while, the recording of the event ends and we add it to the list of events. In addition, the causality inference compares the new event trace with the traces of previous events and updates the causality graph accordingly. Lastly, we take a snapshot of the room right after the event to update the current background. Based on the triggers of the causality graph, we can hide parts of the room from the user that are not up to date. We do this by simply masking those regions in the RGBD stream before passing it to the environment renderer. Using the inverse of this mask, we render the triggers as glossy shapes. Taken together, the masking allows the user to already interact with objects even though not all regions are in sync yet. The other input of the system consists of the RGBD streams that capture the area close to the user. In the case of our prototype, those frames come from the rear sense attached to the Oculus, as well as the Kinect that points to the user's desk. We always render the point clouds from those streams so that the user can interact with handheld objects, for instance. The RGBD frames are also the primary input for the playback scheduler. Based on the causality graph, the scheduler checks whether the user approaches a trigger and initiates event playback of the requested event plus any causal dependencies. If one object is related to multiple events, then those are played back one after another. If all events are played back, the user is in sync again. This concludes our presentation about asynchronous reality. Thank you for your attention.